notes from yesterday. So our objective is going to cover what we didn't get to yesterday. So our objective is going to be representing proportional relationships, direct variations, using graphs. Now this is still out of that Module 3, Lesson 1. So I'm going to write Module 3, Lesson 1. And this time, the personal math trainer we'd written on our other notes, but let's just recap it here. The personal math trainer is going to be on page 75 in your online book. So what I will do today, since you'll have time to work on the homework assignment, is I will use the Elmo, and we'll put up the assignment so you can see it, and then work on it, okay? All right. Oops. So when we're talking about proportional relationships, remember we're basing everything off of this idea. Y equals kx, where k represents a constant. In the problem that we did yesterday, there were 3 miles for 1 league. In some of the homework assignments, there are 7 days in 1 week. So 7 days is what you're always going to get. You're not going to get some weeks have 5 days and some weeks have 8 days. It's always going to be 7. It's constant, okay? The trick is to remember, I need to multiply the smaller guy by the constant to get to the bigger guy. So that's where you have to kind of think, how do I define my y and my x? Okay, and so if I have 0 items, so I had 0 leagues from yesterday's example, how many miles would 0 leagues be equivalent to? 0. So when we're going to graph, we always start at the point 0, 0. Okay? Because that's always going to be the starting point with these. So let's write down a couple things about our graphs. So the graphs will be a line. And the reason why it's going to be line is because of that k value never changes. Okay, so we're always going to increase by equal amounts. So we're going to get a line from this. Will be a line that begins, and by the way, what do we call 0, 0 ordered pair? It's got a name. It's called the origin. So the graphs will be a line that begin, let's write begin, at the origin 0, 0. Okay. Now what is good to do is to start with the table and then take the table parts and create ordered pairs and then graph those ordered pairs. So I'm going to give you a relationship and then we're going to create a table and then we're going to graph it. Yes, ma'am. Actually, I'm not sure it'll go on. No. All right, so I'm going to go to the next page so we can do all this stuff. So what we're going to talk about is the relationship between the weight of an object on the moon and its weight on the Earth. Okay, so we're going to look at the relationship of weight of an object on the moon and its weight on the Earth. So what I'm going to do is look at, let's do from the graph. We're going to go backwards. I'm going to give you a graph, and then we're going to go pick the points out of that graph and then put it into our chart. We can go both directions. We can start with a chart, the table, and graph, or we can take the graph and then create the table. So let's do it this way. So I'm going to bring up my fancy paper. So you guys may need some graph paper, which, again, I have available over here for you. And actually, let me give this a little bit more room. Whenever I'm doing graphing, I need to make sure that I'm labeling accurately my graph. Sometimes we're going to be counting by ones on one axis. We may be counting by a different number on a different axis. Let's see, I want to count by ones on the vertical axis. 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is the Y over here. And then I'm going to count by threes on the next one. 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. So this is my x-axis. So I'm going to just label every other one. 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. And over here, 2, 4, 6, 8, and way up here is 10. The other things I need to do is to label my axes. So the bigger numbers are going to be the weight on the Earth. How do I know that? Say again? Yeah, on the moon, because of the lack of gravity, everything's a lot lighter. So the Earth weight is going to be along the bottom with the larger scale. The smaller scale is going to be the moon weight. Now we're going to compare the weights in the same measurement system, so we're going to also do it in pounds. So I'm going to color in some points that we're going to then take the values and stick it into a chart. So I start at 0, 0, because if you don't weigh anything on Earth, you can't weigh anything on the moon. And then I'm going to go to 6 pounds on the Earth is the same as 1 pound on the moon. And I'm going to go to 12 pounds on the Earth is going to be the same thing as 2 pounds. And then I'm going to go to 18 pounds on the Earth is going to be the same as 3 pounds. And let's go to 30 pounds on the Earth is going to be the same as 5 pounds on the moon. So then I can connect those up. Okay. And this relationship would continue as long as I wanted it to continue, because there is a constant change when you're calculating your weight on Earth versus your weight on the moon. Okay. So from here, let's take those ordered pairs and let's make a chart out of it. So we're going to start with the reference point we understand, which is the Earth. So we're going to call weight on Earth. And we're going to compare it to weight on the moon. Okay, and let's start with the first value that is not 0, 0, because that's kind of boring. So we were 6 pounds on the Earth, and what do we say we weighed on the moon?
2.
Looks like 1. Okay. When we were 12 pounds on Earth, we weighed 2 pounds on the moon. When we were 18 pounds on the Earth, we weighed 3 pounds on the moon. And then we jumped up and we said, well, when we weigh 30 pounds on the Earth, we weigh how much?
5.
We weigh 5. Okay, so that's our table. Now, the reason why we're going to do this table, because I want to write an equation of this information. And so what I need to do is figure out what that constant is. What is constantly going on? So how we do, now look at how the chart was. Earth on the bottom, moon on the vertical, okay? When I want to do my ratios, I'm going to take the moon weight and put it over the Earth weight. Sophia.
My answer divided by 6.
So when you do it that way, that's 1 divided by 6. So I get where you're saying,
Oh, you multiply.
yeah, but that's right. Remember what our equation is: y equals kx. So it's got to turn it into a multiplication problem. So that was the first one. The second one, we had 12 over 2, which guess what? What is it simplified down to? Not 1 over 6.
6.
6 over 1, okay? And then the third one was 18 over 3, but guess what it simplifies to? 6 over 1. And then the last one was 30 over 5. Guess what it? So basically, we're getting two things when we're looking at the ratio. Number one, we're seeing that the ratios are all the same, so we're figuring out what our constant is. Oops, sorry. I wrote those all backwards, didn't I? I wrote those all backwards. Yeah, let's try that
It should
again.
all be 1 6.
It should all be 1 6. I'm so sorry. I'm sorry. Let's try that again. So it was 2 over 12 equals 1 over 6. And 3 over 18 equals 1 over 6. And 5 over 30 equals 1 over 6. So two things. We're proving that the rate is constant. We're always getting 1 6. And we're also discovering what the k value is, what that constant for the proportionality is. It's 1 6. So now if I ask you to come up with the equation, what do I multiply 1/6 by? Do I multiply the weight on the moon by 1 6 to get to the weight on the earth, or do I multiply the weight on the earth by 1 6 to get to the weight on the moon? Okay, so I'm going to multiply 1 6 by the weight on the moon. Is that what we're saying? Okay, so let's look. So if what I'm multiplying is the weight of the moon, well, this is what you guys told me, so now I got to look. So we're saying 1 6 times 1 equals 6?
No, it's
Yeah.
way on the earth.
So it's weight on the earth. Okay, well, I'm just going with what I heard. So the weight, I should say on Earth, y would equal the weight on the moon. So you're basically trying to figure out, how do I get to the weight on the moon if I know the weight on the Earth? Well, I have to take the weight on the Earth and multiply it by a fraction to reduce down. So how we would take this is take the weight on the moon, is what we're going to end up with, is equal to the constant, which is the 1 6, times the weight on. Y equals 1 6x. 1 6. Because remember, that was our ratio we got every time, 1 6. Okay, Joey, you need to draw so that you get a line. I'm seeing a little bumpy in your thingy, so that's why graph paper is so vitally important, so that we don't get bumpy lines, because then they're not lines anymore. All right, you guys good? We're going to do one more together. All right, so here's this one. I'm going to give you a graph. On the bottom scale, we're going to count. Every 2 is counting by 5s. And then on the other scale, we're counting by 2s. Oops, sorry. That's not what I wanted. We take him. That should be counting by 2. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So this is my y-axis, this is my x-axis. Now on the bottom, this is time. And time is measured in hours. So notice that I give 2 labels. One is what is it in words, and then what is the unit of measure. This one's going to be distance in miles. let's say distance. And we'll say miles. And then overall, what are we looking at? And it's going to be called hiking distance. Okay. So I'm going to put boldly some dots. So we're going to start always at 0, 0, because if you aren't traveling time-wise, you're not going to cover distance-wise. So we're going to go, this is our first one right there. So 5 time and 6 on the distance. And then we're going to go, the time is 10 when the distance is 12. And then when the time is 15, we're going to go to distance of 18. We connect these up. Okay. So let's look at, this is the amount of time a backpacker hikes and the distance that's traveled. So the first question we might ask is, what does the point five, 6 represent? So that would be the lowest point, not the 0, 0, but the lowest point that's on there. So what would that actually represent in words, the 5, 6? Joy? But what does it represent in this specific one? Be as specific as possible.
The distance he traveled in 5 hours.
Okay, well, how far did he travel? I agree with what you said, but let's be specific. Okay, so this represents that he traveled 6 miles in 5 hours. Okay? Now, that makes me wonder if perhaps there's a relationship going on between how long he travels and how far he travels. In other words, did the backpacker walk at a constant rate? So let's explore the others. Walk, hike, same thing. So if we have the next point is 10, 12, let's see if we could see if that would work out. So I'm going to go the distance he traveled over the time he traveled. And that, reduces to the same thing. We had that up here, right? Distance he traveled over the time he traveled. All right, let's try another point. Let's see. Time is 15 when distance is 18. So is the distance he traveled over the time he traveled. See, they have a 3 in common. And notice I came up with the same ratio every time. Okay? And here's how I know how to set this up. Is because we want to know the how far he ends up traveling. Okay? The length of time is going to dictate how far he travels. Okay? So for us, keeping this in mind, what I'm going to multiply this ratio by is going to be the time. Time hiking. The y is going to be distance traveled, or distance hiking. So when I write my equation of this relationship, the distance that he hikes is equal to the ratio 6/5 times the time he was traveling. And the reason why I have to put it that way is so that I am always getting, the distance number is always greater than the time that he's traveling. And so that would be the ultimate answer, is to get to there.